Hi. So, in an effort to keep children safe and uneducated, YouTube decided to age restrict this last video because I touched electricity. So I decided to cut that experiment and redo it with something other than my body. If you have watched that old video already, jump to
minute 241
to watch the replacement clips. Otherwise, keep watching. I was talking to my friend the other day about that I had to change something in my breaker panel on a 120 volt breaker, and he was like, be careful with the 120 volt in the breaker panel because that 120 volt is much stronger than the 120 volt on an outlet. I was like, what is the difference? The 120 volt is 120 volt. It doesn't matter if it's in the breaker box or in an outlet. And he was like, no, that 120 volt in the breaker panel powers the entire house. It's much stronger. I was like, what are you talking about? It's 120 volts. Even my daughter knows that the 120 volt across parallel circuits is 120 volts. And it doesn't make a difference. It powers the entire house. It can deliver so much current. And I was like, it doesn't matter how much current it can deliver. It's the voltage across your body that dictates how much current passes through your body. Then he said there are reports of people who worked in a shopping mall, for example, on the 120 volt system that powers the entire mall, and some of them just electrocuted to death. And I was like, it doesn't matter if the 120 volt powers an entire mall of America or just charges your phone. It kills you the same. And then he said, at least when you are working your breaker panel, make sure everything in your house is off, because if they are drawing current, it will get you even worse. And I said, it doesn't matter if something else is connected to the 120 volt and is drawing current. Then he said, of course voltage is the same, but it's the current that kills you. Well, of course I'm not here to downplay the dangers of 120 volt power line. It's very dangerous and in some situations can cook you easily. Especially in some countries they don't even have 120, they have 220 and above, which is even more dangerous. But what do you think? In fact, I don't care what you think. It's a fact. 120 volt is 120 volt. Let me show you something. I have shown it to you before that if the current is running elsewhere, it doesn't affect your body. But you might say that that test was done at low voltage, not 120 volt AC. So I brought here a space heater that runs on 120 volts, and I'm gonna plug this in and run it at maximum power. And my current meter shows that it is running close to, can you see that? Close to 11 amps through the wire into the space heater. So now I'm gonna Here's the replacement clip in which I'm connecting a 10 kilo ohm resistor series with my ammeter across the same power lines that my heater is connected to. So I can see if the 11 amps running into the heater has any effects on the current running through my 10 kilo ohm. So I guess we just plug it in and measure the current. At least it's not my body anymore. Let's use a bit of a higher power 10 kilo ohm resistor so it lasts a little longer. And we plug it in and do the test quickly. Right now the heater is off, and as you can see the current through it is almost zero. And oh no. And the current through the resistor parallel to it is around 12 milliamps as it should be. And now if I turn the heater to maximum, the current running through that is around 11 amps. And yet, the current through the resistor remains at around 12 milliamps. So there is no difference. If the current runs somewhere else, damn it. The current running into the heater doesn't affect the current running through your body if you're parallel to it. Let me show you the voltage through the plug. That is 112 volts, and if I disconnect the load, it goes back up to 120 volts almost, which means that when you draw a ton of current from the power line, the voltage actually drops because of the resistance of the wires, which makes it a little bit safer. You are way better off experimenting stuff virtually through my sponsor Brilliant. Brilliant is a great place online to learn such a variety of lessons on math, science and computing interactively. And you can try all of it with the 30-day free trial through my link below. More at the end. Anyway, I'm not talking about different voltage levels. If you're in your breaker panel or in a mall in their electrical room, there could be different voltages like 120 volts, 240 volts, or even more that can hurt you much worse. I'm talking about the same voltage powering nothing or a space heater or the Mall of America, and that it doesn't make a difference because the voltage is the same and the current going elsewhere doesn't affect you. Unless I'm thinking there could be a way that the resistance or impedance of the lines end up hurting you depending on the load you connect to it. I showed you the voltage of the line can drop when there is a ton of current running through the wires into a load because of the resistance or impedance of the wires. But what if the load is different? What if it's not just the consumer and is some sort of generator? I mean, it could be some sort of inductive load like a solenoid or a motor or some sort of generator that would push current back into the lines. Normally, you would expect the current to go back into the city, but now the resistance and impedances of the wire block the current, which means the voltage on your side could jump up and rise above normal and be more dangerous. Where's a good dangerous load when you need one? Say hello to my little inductor here. Let me plug in the 120 volts. And I'm just probing the power line right now. It's not connected anywhere. And you see a regular sine wave on the scope. Although you see some wiggly higher frequency components riding on the sine wave, which is an indication of other loadly behavior on the power line. Now if I connect my inductor to the power, well, you see the sine wave is not changed at all. An inductor alone drawing current from the power lines will just cause the voltage to drop as well. It's when they're switching that is the problem. Which means I have to connect and disconnect. Well, let's see what happens to the sine wave when we do this. Oh, look at that spike. Oh, this is not bad. Let's try again. Ooh, look at this. Now this is what I'm looking for. Look at that. It's jumping up to 500 volts. And it's pretty high frequency too. Wow, look at this high voltage, high frequency stuff. Although this is just a very momentary burst of high voltage. But I mean, imagine some sort of powerful device was continuously putting these things on the power lines. I mean, if there is a device like this that is putting such huge bursts of high energy pulses onto the power lines, it is horribly failing all the standards in existence. There must be proper filtering and noise cancellation and things of that sort. But I don't know, maybe in some higher energy demanding facilities like big factories, such bursts of energy are acceptable. Let me try something. I put a piece of copper here and I'm gonna cut between these two pieces a very small gap, and I'm going to connect these two to the power lines, but because there is a gap here, it's not going to short them. I think the tiny cut between the two plates is enough to not allow the 120 volts to arc across it. I need to make the tiniest gap possible without them touching. Are they not touching? I don't think they are touching. Let's see. Nope. They're not touching. Should be enough not to allow 120 volts to arc over. So my tiny gap is connected across the power line, but the inductor is not connected yet. Let's plug it in and see what happens. I think I made it too close. Well, I guess the gap is wider now. Let me explain to you what I'm trying to test here. I'm thinking if I make a tiny gap that the 120 volt itself is not high enough to jump across, then perhaps these high voltage generated noises on the lines are high enough to arc through the barriers and create a momentary arc that now the 120 volt itself is able to maintain by pushing energy through it. And that way, these noises become much more dangerous and damaging and a fire hazard. Let's readjust the gap. Okay, they're not touching. Trying again. Good. Now the gap is wide enough not to allow the 120 volt to arc over. Now what I really like to know is what happens if I connect and disconnect my inductor. Let's try it. Nothing? I was hoping the higher voltage would arc over. It is such a tiny gap. Is it even powered? God. Well, let's connect the probe and see if the high voltage is actually there. Oh, as usual, I connected the probe ground to live. Damn it. Okay, let's try again. Is the high voltage there? Oh yeah, look at them. They keep appearing. Well, there you have it. Such switching inductances can create a ton of spikes and high voltages. But apparently I'm not able to adjust my gap so precisely so that only when there is high voltage it arcs over. Well, that's the only way I can think of that a specific load like a switching inductor can generate even higher voltage spikes on a 120 volt line so that the 120 volt line can hurt you even harder. But this is not normal. I mean, all consumer electronics and appliances must have proper filtering on them to avoid this kind of noise. And in huge factories that might have all sorts of strange loads that can create this kind of noise, the power cables are so thick and low resistance and impedance that they would just eat through all the noise. For example, here's a vacuum cleaner connected to the lines. And if I turn it on and look at the sine wave, no difference. There is no additional noise on the power lines. So this shouldn't be a problem at home anyway. The only thing I can think of is that, say you have a crappy corded angle grinder or drill that has these brushed DC motors that create a lot of noise, and you plug it somewhere far away from a breaker so the length of the power wire is very long so that it has high resistance and impedance. So those devices create a ton of noise locally on the power lines. And the power line extends from there to somewhere else that somebody is playing with, and they accidentally get a shock from the noisy 120 volt power line, which might be much more painful and dangerous because of those bursts of high voltage, high energy noise on the power line. This is the only way I can think of that something plugged into the power can help you get electrocuted even worse. And it's not related to if it is in the house or in a mall, although mall being much larger makes it more probable that something dangerous is plugged in and can electrocute someone somewhere else. You let me know in the comments if there is any possibility that I might have missed. But perhaps instead of shoving something into the power lines to teach yourself a lesson, consider the much safer, electrocution-less, and interactive way of learning that is my sponsor, Brilliant. The new year is upon us, and with it, tons of new opportunities, which also means new things to learn. But imagine in your own time you grow into a better thinker and problem solver and more knowledgeable and skilled. You are imagining using Brilliant. Imagine not having to drag your feet through the hard subject you need to learn. That's what Brilliant does for you. Because from my own experience, when you need to learn something and try Brilliant for it, Brilliant pulls you along with its thousands of fun and interactive lessons. Like a good teacher, it makes you feel smart, capable of absorbing even complex concepts. So you keep wanting to go back to see what's next and how you can surprise yourself by learning something you thought you couldn't learn. All done through personalized quality lessons that start where you're comfortable and take you to the higher levels. So don't be slacking. Use my link brilliant.org/electroboom to get a 30-day free trial in which you can speedrun a ton of lessons. But like I said, learning is made so easy there that you don't want to let go. No worries. My link gives you 20% off Brilliant annual premium subscription, so you can learn forever and enjoy the person you become. And thank you for watching.